Dr. Muhammad, and this is another class under dynamics of structures. Still we are talking about multi-degree of freedom systems, MDOF, and today I'm going to talk about modal expansion of displacement. So it is an important topic for multi-degree freedom system in general, and I hope that we can understand it well together. Start with the definition, or we can say the understanding of modal expansion of displacement. What does it mean and how we can deal with it? So let's put this statement in the beginning, which is related to the modal expansion. We can say that for any set of n independent, take care of this word, independent vectors, any set of n independent vectors can be used to represent any other vector of order n. So the meaning of this sentence here can be given using this equation. The point is, if we want to represent this vector, okay, this vector, it's any vector, okay, let's assume it is a vector of displacement, for example, in our case, which is related to our case, vector of displacement. So we have like u1 of t, u2 of t, for example, u3 of t, something like this, if we're talking about 3 degrees of freedom. So we are claiming, using this sentence that we have stated now, we are claiming that this vector can be represented by a set of n independent vectors. So we need to have n independent vectors, which is going to be in this form, which is the first vector, for example, let's assume it qr, times a scalar quantity, it is qr. So we're going to have the vector, one of the n independent vectors, multiplied by this qr. And then we're going to have the summation here. Summation from r equal to 1 to the n, or the number of n independent vectors. So this is what we claim regarding the modal expansion in general, which means that any vector that we have, we can say that there is another vector, okay, let's assume it q1, for example, multiplied by one scalar quantity, which is, we call it q1, for example, plus another vector q or phi2, for example, here, multiplied by q2, and so on and so forth for the n independent vector, for n independent vectors. If we have 3 degrees of freedom here, for example, or 3 elements here, then we are going to have q1, q2, and q3, and we are going to have phi1, phi2, and phi3, 3 different vectors in our case. Okay, so this is what we are claiming to have here. Okay, so let's go a little bit into the understanding of this equation and go through it in a better way. So here, let me check something. So here we are going to say that n, which is the degree of freedom, we're talking about the degree of freedom here. So in this case we are going to have n degrees of freedom. If we have 3, then we are going to expect these vectors to be 3 vectors. Okay, remove this. Okay, and here if we have qr, it is going to be n qr's. Okay, so it is n scalar multipliers, and we are going to call this qr to be a scalar multiplier, and in our context we are going to give it this name, which is modal coordinate. Okay, and for many of them it is going to be modal coordinates. What is the meaning of modal coordinate? We are going to understand the meaning of this word later. Okay, it is like a weight for this mode that this qr is associated with. So we are going to say that if we have mode 1, for example, it is going to be multiplied by a scalar multiplier called q1, and it is going to be as if it is like scaling this mode in order to give the contribution of this mode into the total response of the system. Okay, so that's the meaning of modal coordinates. And I put here for example only to understand if we have like 3 degrees of freedom. This is for 3 degree of freedom. If we have u1, u2, and u3, and this is, let's assume that it is variable with time. We are having t here, which is the displacement of the first story, second story, third story, if we're talking about shear building, for example. So based on equation 8, based on the theory of modal expansion of displacement, we are going to claim that we can bring 3 different independent vectors. Let's assume these vectors are phi1, phi2, and phi3, which are the mode shapes that already we have explained about them before, right? These mode shapes, they are going to have the amplitudes inside the vector, like phi11, phi21, phi31, and so on. And then each mode shape is going to be multiplied by the associated scalar multiplier, its associated modal coordinate. Then it is going to be multiplied by it. And then phi2, it is the same. It is going to be multiplied by q2 plus phi3 times q3. Okay, so now I think that the question that going to pop up in your mind is what are the values of this q1 and q2 and q3, and how we can obtain it, how we can get it. We have unknown here. Okay, actually we are going to see later that if we want a specific output or a specific response or displacement response, we can obtain this q1, q2, and q3. Okay, so it is based on what is the output that we are expecting, or what is the output that we can obtain here, okay, or we can assume, for example, here. Then I am going to tell you, for example, if we have u1 and u2 and u3, it is like 1, 2, and 1.5, for example. Let's assume this is the u1, u2, and u3 here, which is the displacement. I'm going to tell you that this 1, 2, and 1.5, this vector of displacement, it is going to be like q1 times the first mode shape, q2 times the second mode shape, q3 times the third mode shape. Mode shapes, we can obtain them easily from the previous lectures if you visit, okay, with their associated natural circular frequency omegas, right? So omega q1 and q2 and q3 here are going to be unknown for us. Today we are going to know how to obtain this q1, which is the modal coordinates, okay, using our technique for, or what we are going to explain for today. Okay, I hope that the picture to be clear for you, and I hope that you could understand that what is the main function now of this modal expansion or this modal coordinate, and the meaning of modal expansion in general. Okay. Okay, I think that the next question that is going to be popping up in your mind is what we are and how, what is the benefit of this, right? What is the benefit of knowing about this modal expansion? I'm going to tell you about the benefit of this modal expansion in like 5 minutes, but before that I want to multiply equation 8, okay? I want to multiply equation 8, the previous equation, by the phi n transpose times the matrix M. Okay, both sides. So we are going to put this phi n transpose M times u here, which is the displacement, okay, vector, and then we are going in the right hand side, we are going to put the same, we are going to put phi n transpose times the matrix M as they are here, and we put them QR as it was in the equation, and all of it, they are multiplied by QR. And do not forget the summation here. We have the summation from n equal 1 to capital N. This is the number of degrees of freedom that we have. Okay, so if we have like 3 degrees of freedom, then n should be 3. And we are going to have 3 different mode shapes in this case. Okay, look to this part, phi n transpose times matrix M matrix, mass matrix times phi r. Doesn't that remind you with anything that we have explained before? Exactly. It is the orthogonality condition with respect to the matrix M. Okay, if you do not understand what is the meaning of orthogonality condition and what is the significance of it, then please visit the previous videos and you're going to have a full picture of the meaning of orthogonality condition. Okay, based on that, we are going to see, that we have here that for all different phi n and phi r, n and r, this means that different mode shapes. We are having different mode shapes. We are having different mode shapes. Okay, so in this case, what we are going to have, if we are having different mode shapes, the summation above is going to be 0. Do you remember from where we got this? From the orthogonality condition. Do you remember when I said to you before that orthogonality is going to make our life easier in terms of the computational effort? And this is true, and it comes true now, because we are finding that this term, which is highly complicated, is going to boil down to 0. Okay, so this means that all of the thing here between the parentheses going to be 0. And based on that, the computational effort is going to be easier for us. Remember, for any two mode shapes not identical, remember, not identical, they are different, okay, not identical, like n and r, for example. Here, what do we have here? Phi n transpose times mass matrix times phi r equal to 0, right? This is the orthogonality condition. Okay, and this summation is going to be 0 as long as n and r, they are different. But when n and r, they are the same, then the summation would not equal to 0. Okay, so in this case, only when n equal to r, we are going to have phi n transpose m times phi n. It is going to equal to 1 if normalized modes are used using the normalization factor. Do you remember? If you do not remember what is the meaning of normalization factor and normalization in general of mode shapes, please visit the previous lecture. So it is going to be 1 if we are going to use normalization or normalized mode shapes using the NF. And otherwise, if we didn't normalize, then it would not equal to 0. It wouldn't equal to 0 if we are having the same mode shape, because omega is the same. If you remember in the orthogonality condition, when we were talking about orthogonality condition, they should be different in order to equal to 0, with one condition, that this mode shape different than this mode shape and their omegas. Do you remember when I was writing like this? Omega n does not equal to omega r. Please visit this video for the orthogonality condition with respect to m and with respect to k. This is the main condition, that we do not have the same eigenvalues, we do not have the same natural circular frequencies, we do not have the same mode shapes. Okay, this is the main, we can say this is the main condition that we having. Okay, so this at the end, we can say, let's clear everything, this term would not equal to 0 if we are having n and n, if we have the same mode shape. For the same mode shape, this multiplication is not going to equal 0, and it would equal to 1 just in case of normalized mode shape. Otherwise, no, it would not equal to 0. It will have number. Okay, okay. So now I think that it's okay for us. Let's go to the next slide and understand more about this. Okay, so here we have, let's put the equation again. After removing the part of the zeros, we do not have the zeros here. The left hand side, it is going to be the same, right? No problem here. Phi n transpose times mass matrix times u, which is, this is the displacement response that we are seeking for. Okay, the displacement response, do not be confused. U is different than phi. Phi, it is mode shape. Mode shape. Okay. However, U, it is the response of the structure, that is we are seeking for. Okay, this is the response of the structure, which is U1 of t and U2 of t and so on. Okay, equal to the right hand side is going to be phi n transpose times mass matrix times phi n. They are the same. This is the only remaining term, because plus blah 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 here it is other terms, but all of them, they what? Like phi n times m, okay, times, this is transpose, and here phi r, for example. So we're going to have them zeros, right? So everything already moved here, and the remaining part is this part times QR. Okay, so we want to obtain QR. We want to know what is QR. So again, what is the meaning of QR? It is a scalar multiplier, multiplier. We call it modal coordinate. It gives to us how much the mode shape is going to contribute to the total response of the system, of the structure. This is the meaning of it. Okay. Okay, so we are going to put everything on the right hand side and putting only QR to be on the left hand side because we want it. So QR equals to, this is the previous left hand side, it is going to be in above here, it is going to be in the numerator, and then in the denominator we are going to put this part here. Okay, phi n transpose m times phi n. Okay, so now let's look deeper into this equation. In order to obtain QR, the modal coordinate or the scalar multiplier or the ratio or the weight of the mode shapes contributing to the modal contributing to the total response, we need to know different things. Actually, three main things here. As you can see, we need to know mass, right? Mass matrix should be known. Another thing, we need to know phi n, okay, which is the mode shape. It is transposed here, but it's the mode shape. And also it is phi n here. It is not transposed, but also it is the mode shape. So we need to know, first, it seems that we need to know phi n. So we need to know the mode shape vector, okay, the amplitudes. So the first thing, or the first step, is to know the mode shape. And this is, as I said many times, the first step in everything that you are doing for multi-degree of freedom system, that you need to get phi n and omega. It is always the conjugate, the eigenvalue problem solution, okay, the eigenvector and the eigen problem. So this is already, as I said, known for us, and we can obtain it. Okay, so based on that, we are going to have here, in this case, we need to know phi n. So to get QR, we need to know three things. First, mode shape vector. Already we know it from the previous lectures, how to obtain it. The mass matrix, the second term, it is known for us, given for us, no problem or no calculation for it. It's given, commonly it's given. And the third one is the displacement responses vector, which is U. Okay, we need to know it. We must know it in order to get QR. Okay, so actually here means that if I said to you that U equals to, for example, 0.5, 1, and 0.3. Okay, this means that we need to know the response or displacement, or this displacement responses vector, in order to tell you, well, from the first mode shape, if the first mode shape, for example, let's assume it is like 0, 1, not 0, it is like half, 1, and like 2/3, for example, something like this. Then I'm going to multiply it by something here, QR. Okay, so this is Q1 because it is related to the mode shape number 1. So what is the value of this Q1? If I said to you that it is going to be, for example, it is going to equal 0. Okay, if I calculated and found this Q1 equal to 0, this means what? This means that the first mode shape is not going to contribute at all in this displacement vector. Okay, okay. If I said to you, for example, that it is not 0, it is 1. Okay, in this case, the whole mode shape, number one, is going to contribute to the displacement response vector, okay, and so on and so forth. So it depends on, if we have here, we have 3 degrees of freedom, so expect that we are having another 2 terms here related to Q2 and Q3. Okay. Okay, let's clean everything here and let's move on and move forward. So now let's have some notes here that it's going to help us a bit about the importance of the modal expansion of displacement vectors. So again, the word importance should always be in our minds. What is the importance of this modal expansion? Okay. Number one, this concept will be used to obtain solutions for free vibration response of undamped systems. So actually we are going to work on the undamped system in the next video. So we are going to see that this modal expansion is going to make it easier for us to obtain the undamped or to solve the free vibration response for the undamped system. So this is an important issue, because maybe it's not very convincing to you to tell me that, well, if you're going to give us u, or this u which is u1 of t and u2 of t and so on, then how we are searching for this. So now you are telling me that I want to get QR, right? So what is the point here? Which one that we want to find? Yes, I understand this question in your mind, but the reality is we are going to make a relation now between the two, and then we're going to use this relation for this, which is the solution itself. We're going to find that this is going to make it easy for us for the solution of the free vibration, okay, of undamped system. And number two, it is also, this concept plays a central role in the analysis of forced vibration response and earthquake response of multi-degree freedom systems. So we are, in general, whenever that you are dealing with forced vibration response for any dynamic system and earthquake response, you are going to find that it is really a pivotal concept or an important concept and plays a central role in the analysis there. Okay, as I said, sometimes for multi-degree freedom system you will find that we need to find a way to simplify the analysis. Okay, so that's what we are seeking for during these different lectures and so on. We're going to, because as I said, DOF degree, the multi-degree freedom system, it is dealing with different, as if we are dealing with hundreds of single degrees of freedom. So we need to find a way, a computational way that efficient enough and practical enough and easy enough for us to handle. So this is why we come, like we are going around the main concept by some different things or different concepts, like this modal expansion, for example. And then you're going to find that it gives us a great tool actually, and simplifies the process, whether for analysis or for the solution in general for different system, whether undamped system, forced free vibration systems, or for earthquake response systems, and so on. Okay. Okay, I hope that you understand what I'm saying till now. Okay, so bear with me, and we are going to find something interesting. Yes, in a minute we are going to explain what I have mentioned before. Let's understand what we have explained through an example. So in this example, as you can see, it is a shear building here, and in this shear building we have, in the first story it is 2m, this is the mass, and the second story it is m. Okay, so we have different masses here. For a two-story shear building having phi 1, it is the first mode shape here, equal to half n1, and the second mode shape it is -1 and +1. Okay, imagine this. So this is how the first mode is and what is the second mode is. Well, now determine the modal expansion of the displacement vector. Of the displacement vector 1 and 1. Okay, so now it is given for us. Okay, now this is the example is generous enough for for us. It is giving for us the U. Okay, it says to us if this system is going to move 1 unit here and 1 unit here. Okay, so this mass is going to be like this. Okay. If we assume that this system is going to move like 1 unit here and 1 unit here, what is the contribution? What is the contribution of phi 1 and phi 2? In other words, what is the modal expansion of the displacement vector based on mode shape 1 and mode shape 2? Okay. Okay. Now let's go and see. Okay, the solution. First of all, we're going to look to QR. Okay, QR, how we can calculate it. How many QRs that we have here? Exactly, we're going to have Q1 and Q2. We have 2 mode shapes, right? We have 2 mode shapes. So we have Q1 and Q2. We are going to calculate this QR 2 times. We're going to calculate it 2 times. As usual, you're going to find that everything is the same. Mass matrix here, the mode shape transpose here, the mode shape here, and this is the modal. This is not modal. Remember, this is the response. Okay, given response. As I said, it is 1 and 1 for this example at least. So it is given for us. So now we can understand that everything is given for us, right? Okay. So if we're going to talk and put it in terms of an equation, so we are having here Q1, so it equals to phi n transpose, means that half and 1, because already phi 1 we said that it is the first mode shape, it is half and 1, putting it like this is the vector, and then we have mass matrix, which is going to be 2 degrees of freedom here, and we have only the diagonal terms, elements. They are 2m and m. However, the off diagonals, they are zeros, as we know, for the mass matrix. And then this is u, which is the response vector. 1 and 1, this is given for us. Okay. And then in the denominator here, we are going to have the same phi n transpose, half and 1, the same matrix, mass matrix here, and then we are having half and 1 here, which is phi n. It is here. Okay, phi n. Okay, so in this case, we are going to calculate the values that we have here, and we are going to find that we have, let's clean, and here we are going to have Q1 and Q2 to be in this way. So Q1 after calculation, so we're going to multiply first here we have 1 and 1, so everything is going to be the same. We can like as if it is multiplied by 1 here. So we have half and 1 times 2m and m here. So if we are going to multiply this matrix with this vector, it gives us this vector 2m and m here. Okay, so and then half times 1, sorry, half and 1, and we are going to multiply this vector by this one. So half times 2m, it gives us m. 1 times m, it gives us m. In a similar fashion, we can do in the denominator, half times m, it is half m, 1 times m, it is m, and then we can simplify it, and we can obtain 4/3 here, or 4 over 3, 1.333, for example. This is Q1. Okay, and Q2 in a similar fashion, we are going to give the same, everything will be the same except that, exactly, the mode shape is going to be the second mode shape, -1 and 1, here -1 and 1, and here -1 and 1. But everything, the mass matrix is the same, the response vector, it is the same. Okay, so take care of the mode shape that you want to substitute here. After making these kind of calculation, it's easy for you. You can do it better than me, and you can find that at the end we got this value. So this is Q2, this is Q1. Again, do not leave the basic principles obscure. Q1 means modal coordinate, means scalar multiplier that is going to be multiplied by the first mode shape. Q2 the similar, It is similar, but it is going to be for the second mode shape. Okay, now let's go. Let's clean first and go after that. Okay, for us here, we have the system that I want, or the point that I want to highlight here is that our system has response. This is U, okay? This is U, 1 and 1. This is given for us here, right? And if you put it, we have the mass here, 2m, and here m. It moves 1 unit here, 1 unit here, according to our displacement response. And the coordinate, or in this degree freedom, and this is degree freedom 1, this coordinate 1, and this is coordinate 2, which is degree freedom 2. They are the same. Then the modal coordinate, here this comes from here. Do you remember when I said to you I'm going to explain to you what is the meaning of modal coordinate? Here comes the point. This degree of freedom, we call it coordinate, okay? Degree of freedom means the coordinate. This coordinate, coordinate 1 and coordinate 2. So the modal coordinate is going to be the multiplier of the modal coordinate, which is q, okay, is going to be, this is q1 multiplied by mode shape 1, which is phi 1 here, half and 1. If we multiply it 4 over 3 times half and 1, 4 over 3 times half, it would give us the first coordinate here, 2/3, right? 4 over 3 times half, it will give us 2 over 3, right? That's right. 2 here, and this is going to be 2, so we are having 2 over 3 here, 2/3, and the first coordinate. The second coordinate is going to be 4 over 3 times 1, so it is going to be 4 over 3, right? This is the second coordinate. Well, so the first mode shape need to be modified by 4 over 3 in order to give us this amplitude, as you can see here on the screen. 2/3 in the first coordinate, 4/3 in the second coordinate. And then it's going to be multiplied by, it's going to be added or superimposed by the second, or the contribution of the second mode. The second mode is going to be like this. Minus 1 over 3, what is this? It is Q2. Remember, Q2 that we have done. Okay, so the Q2 minus 1, minus 1/3 times minus 1 and 1, which is the mode shape number 2. Minus 1 over 3 times minus 1, it's going to be 1/3. It is positive here. Take care of the sense, positive going to the right. And then it is minus 1 over 3 times 1, it is going to be minus 1/3. So take care of the sense, it is going to be minus if we say that. Here is positive, here is negative. Okay, so here, minus 1 over 3. Minus 1 over 3. What is the meaning of this? What is the meaning of this? If you are going to sum up the coordinates that you've got coming from each mode shape, you are going to find that the mode, or you're going to find the total response vector is going to be the same. Can you superimpose minus 1/3 plus 4/3? It gives us 1. And then plus 1/3 plus 2/3, it is going to give us 1. That's the point here. So the contribution from the first mode is going to be, as you can see here, in the first coordinate 2/3, and the contribution from the second mode for the first coordinate is going to be 1/3. Okay, so 2/3 from the first mode plus 1/3 from the second mode shape. This is the contribution in order to give us 1 for the first degree of freedom, or for the first coordinate. And for the second coordinate, we are going to have minus 1 over 3 plus 4 over 3, okay, in order to give us 1 also for the second degree of freedom, or for the second coordinate. Okay, do you understand this? The numbers here, it makes sense, because in the second coordinate we're going to find that the first mode is going to contribute highly, okay, is going to contribute highly. So let's, okay, so here I think that the meaning, we can understand it clearly now. that we have like the contribution of the first mode is going to be 4/3. However, the contribution from the second mode is going to be opposite to it. Okay, it is opposite to this. Like the first mode wants to go to this direction, the second mode is going to bring you back with this direction with this amount. This is 1/3 here, this is 4/3 here. Okay, 4/3. Okay, and in the similar fashion, let us clear everything here. So yes, so here that's the meaning what I said here, that we are going to move here. The second mode is going to move like 4/3 here, and the first mode is going to go in this direction 4/3. The second mode is going to go in this direction by 1/3. So the total of them is going to give us 1. However, for the first mode, we found that we're going to go to the right direction 2/3 and going back by 1/3. So it is going to be like this. Like this is 2/3 using the first mode. However, the second mode is going to make it half of it, 1/3. Okay. So we can say that from this, we can say that the first mode is going to contribute larger to the first or the second coordinate, which is degree of freedom number 2, because like 4/3 is going to be exerted by the first mode. Only 1/3 is going to be exerted by the second mode in the opposite direction, right? However, here in the first mode, we're going to find in the first degree of freedom, we're going to find that first mode is contributing by 2/3. However, the second mode is contributing by 1/3 only, almost half of it. Okay, so here first mode is almost double the second mode with opposite direction, as we said. Here in the degree of freedom number 2, the first mode is going to be 4 times contributing 4 times higher than the second mode. Okay, so the first mode is going to be 4 times the second mode contribution, and of course we are keeping in mind that we are in opposite direction. No, I'm sorry for this. I think that I have a mistake here. Yes, 2/3 and 1/3. Sorry for this. So for this point, I'm sorry for this. We are not in the opposite direction. Okay, forget about this. Let me clear out. So here we are in the same direction. I'm sorry. So the first mode is going to give us 2/3 here, and after that the second mode is going to give us 1/3. Okay, so I'm very sorry for this. So here, as you can see, they are in the same direction. So the first mode and the second mode, they are in the same direction. Okay, so the contribution from the first mode is almost double that. It's not almost, it is already almost. It is already double of the first, double of the second mode. So the contribution from the first mode is double that of the second mode. However, here it is, as I said, we are moving like 4/3 in this direction, going back by 1/3 in this direction. First mode, this is second mode. Okay, so we can say that first mode and second mode, they are contributing in the same direction. Okay, for degree of freedom 1. However, first mode and second mode, they are oppositing one another. They are opposing one another for the degree of freedom number 2. Okay, can you have, I hope that using this you can have a sense of what is the meaning of the Q1 and Q2. Now, how they are adjusting the mode shape amplitudes in order to obtain the final responses that we want. Okay, I hope that works well with you. I think this is enough for us today, and let's have another lecture regarding the solution of undamped system. Thank you for listening. Let's clean this, and I hope to see you in the next video with the solution of undamped system. Okay. Thank you and see you next time.